So let's talk about momentum's fraternal twin here, something called impulse. So when we go to talk about impulse, a little bit of a review. Remember acceleration? The way we defined it all the way back in the first chapter was the change in velocity over the change in time. But we also had another equation that said what acceleration is, and that was Newton's second law. And Newton's second law said acceleration was the sum of the forces over the mass there. So if both of these things are equal to acceleration, then they're equal to each other as well. So the sum of the forces over the mass is equal to the change in velocity over time. I'm going to do a little easy algebra trick here. I'm going to cross multiply and divide here. And so our next line will look like this. The sum of the forces multiplied by the change in time will equal the mass times the change in velocity. This equation right here has a particular name, which we're going to get to in a second. But let's actually focus on this side first. We give this side a name, and we call this side impulse. So impulse is equal to, often we just write it as force times time. So we get rid of the sum there and we get rid of the change there, but it's basically the same thing. So impulse is force times time. And we usually measure this since force is measured in newtons and time is measured in seconds, Newton seconds. Not newtons per second, that'd be divide, but Newton seconds. Over here on this side of the equation, what about that? Well, mass times change in velocity, what is that? Well, mass times velocity is momentum. So mass times a change in velocity, we can actually move this change in out front, and we can say that this is a change in momentum. That change in is very important. It's not equal to momentum, it's equal to a change in momentum there. So when we write it all out here, we can say it like this, that force times time is equal to a change in momentum. This side is called impulse. Here's a change in momentum. So the name of this concept is impulse momentum theorem. And we've seen something very much like this before. If you remember from the stuff we were doing before spring break, we had another concept. It was force times distance, which we called work. And that caused a change in something that was very similar to momentum. It caused a change in kinetic energy. So this, remember, was called the work energy theorem. So a force times a distance, work, causes a change in kinetic energy, but a force times a time causes a change in momentum. So this is the impulse momentum theorem. Now, something that's really important for later today and going forward for all this stuff with momentum is that, remember then, as soon as you know the impulse, if they give you anything about force and time and you know the impulse, then you also know the change in momentum because they're equal to each other. Conversely, if you know the change in momentum, if you have a mass and you see how much its velocity changed, you'll know how much its momentum changed. And then right away, you'll know its impulse. And so those two things are always equal to each other. So let's just do a real quick example with one of those where we solve a problem like that. So let's say we've got a little bowling ball, and it's a 12 kilogram bowling ball rolling along here. And let's say it's got a velocity of, let's make it easy, 10 meters per second. And then later down the line, you exert a force and you bring this thing to a rest. So a lot of easy questions here. First of all, let's find its momentum 1, we'll call it here, its first momentum. By the way, some books might call this its momentum with a little I for initial momentum, and some books might just call it momentum with nothing to indicate the first one. But any way you do it, it's mass times velocity there. And so when we plug in these two things, that's easy to do. A mass of 12 times a velocity of 10 gives you 120. And remember, the units are kilogram meters per second. So we start off with 120 kilogram meters per second of momentum. Well, here at rest, let's find its momentum 2, or some books may call it its momentum final, or some books call it momentum prime. And for whatever reason, that calling the second thing prime, you only see with momentum. But that would be this mass times this velocity, but there is no velocity here. So it has 0 kilogram meters per second of momentum in the end. So the next thing we can ask is, what is its change in momentum? Well, change in anything is its final minus its initial. So its final is 0, its initial was 120. So this is very important. Our change in momentum is negative 120 kilogram meters per second. The negative indicates our change was towards the left. In other words, we had to have a force to the left in order to do it. So as soon as we know the change in, then we can figure out the impulse, because the impulse is equal to the change in momentum. So right away, without even doing any math, we know the impulse is also negative 120. The units we tend to use are Newton seconds. And then last thing here, let's say we stop this over a time of 5 seconds here. What would be the force necessary? Well, if we already know the number for impulse, we can use that along with impulse is equal to force times time. So we know the impulse is negative 120. We're looking for the force. We know the time is 5 seconds. So if we solve for the force, we'll get negative 24 newtons. In other words, the negative now means to the left, which makes sense. If this ball was rolling to the right, to stop it, you'd have to push to the left.